This is the continuation of our second review session for Chem 112. This is covering chapter 16 and 17. So we'll begin with water dissociation. So if I have H2O, so the question is, if I have H2O and at 60 degree, this is liquid. At say 60 or 70 or one of these high temperatures, say Kw value at say, these are just the number that I'm making, at 70 degrees centigrade, say Kw equals to 16.0 times 10 to the negative 14. Just as an example, I just want to show you how this works. So liquid water at a high temperature gives a Kw value of 16.0 times 10 to the negative 4. Kw is equilibrium constant when water breaks down into H plus and OH minus. So the question is, what is the pH for neutral? We're going to show you that calculation. At room temperature, we know that pH for neutral solution is 7. Now we'll see at high temperature what kind of value we get. So let's set up like this: H2O, liquid that breaks down into H plus plus OH minus. And this is aqueous, this is aqueous. Now let's assume that initially I have concentration of water is A. This is the heterogeneous equilibrium liquid, and then this breaks down into H plus and OH minus. Liquid is present in water is present there in large excess. So this is 0 and 0 at equilibrium. Oh, I must tell you that this is liquid, this is also an aqueous solution, this is an aqueous solution. In that sense, this is homogeneous. But if you look at the species, this doesn't change much because they have a large quantity of H2O. So only there is a slight change because of this breakdown. So at equilibrium, a part of the water molecule will break down into H plus and OH minus. X is the quantity that breaks down. And if one of these breaks down, you are going to get 1 H plus, 1 OH minus because of these coefficients. When 2 H2O breaks down, you get 2 of this, 2 of OH minus. When X of water breaks down, you get X here and X here. Now we can set up an expression, and here you have H plus as well as OH minus. The equilibrium we call Kw equals to H plus times OH minus. You can ignore the bottom part. Let me just, for the time being, show you H2O. That's a pure liquid, and it has so much large concentration which doesn't change much, so you can ignore this. So now we have H plus times OH minus, which is X times X, equal to X squared. So X squared equals to Kw, and let's assume that we already know the value. So Kw is 16 times 10 to the negative 14. That's equals to X squared. So from here we can get X value equals to 4 times 10 to the negative 7. And that's the concentration of H plus as well as OH minus. From here we know that once we know the X, that's going to be the value for H plus as well as OH minus. In order to be neutral, a solution must have same concentration of H plus as OH minus. And that's what we have here. That's why the value that we got is for neutral solution, but at a high temperature. So from here I can get pH. So pH in this particular example is going to be minus log of H plus, and that's minus log. This is base 10, log of base 10 and this is going to be 4 times 10 to the negative 7. So this is just a sample calculation which shows you how to calculate pH of a neutral solution at a high temperature. Okay, so make sure you are familiar with this kind of calculation. At 25 degrees centigrade, that value is well known. Kw value is 1 times 10 to the negative 14. Oh, I think here I made a mistake here. This should have been 4 times 10 to the negative 14. That's what I have used here in my calculation. So this is 16 times 10 to the negative 14, and that's what we have here, 10 to the negative 14, and we took the square root. That's 4 times 10 to the negative 7, and then you get pH value. So the pH value that you'd have would be the pH for a neutral solution at that temperature. So when you talk about pH of 7, we mean pH 7 for neutral solution at room temperature or 25 degrees centigrade. So as you change the temperature, the pH value is also going to change for a neutral solution. So make sure you know this kind of calculation. The next problem that I would like to go over is called common ion effect. This is going to be a qualitative question on common ion effect on pH. So let me explain that to you by giving you 2 examples. Say, one question I'm asking you is, when KBr added to HBr, how will it change pH? So when I have HBr, you know that HBr is a strong acid. Make sure you know which ones are strong acids, like HCl, HBr, HI, HNO3, H2SO4. These are strong acids. What that means is they break down 100%. So question is, I have a specific quantity of HBr in solution. If I add KBr, how is it going to change the pH? So let me show you what's going to happen. Once I have a solution of HBr, since this is a strong acid, let's write down a strong acid, SA for a strong acid, it will break down 100%. So you're going to get H plus and Br minus. All of these will break down. There'll be no left over. So this is going to be 0 at equilibrium. And you would have all H plus and Br minus. Now when you're adding KBr, I want you to know that sodium and potassium salts break down 100% in most cases. Like potassium would get separated in this case as K plus Br minus. So when you, in this solution, when you add KBr is going to break down as K plus and Br minus. So what is the common ion here in these 2 solutions? Br minus. How is it going to affect? Normally you'd think that since in this particular case Br minus is increased, that should move the equilibrium to the left, from right to the left. And some of these H plus is going to combine and you get HBr. If that happens, pH, H plus concentration is going to decrease, or OH concentration is going to increase, and pH should go up if that happens. But that's not the case. Why? This is a strong acid. It doesn't want to stick to H plus. If it does stick to H plus, it's not going to be a strong acid. So in other words, you can't apply Le Chatelier's principle here. So Br minus would have no effect. Why it would have no effect? Because HBr is a strong acid. It doesn't want to stick to H plus. So answer is no effect. So anytime you deal with strong acid, strong base, and if there is a common ion effect involved, there'd be no effect on pH. What would happen if I have a weak acid instead of a strong acid? Let's go over that example. The next question that I would like to go over would be sodium nitrite added to HNO2. So NaNO2 added to HNO2. First, we need to know what kind of compound we have here. HNO2. You need to know that HNO2 is not a strong acid. How do I know that? By knowing the strong acids, like a strong acid which should have hydrogen, nitrogen, and oxygen would be HNO3, not HNO2. So as soon as you see it's not HNO3, but it's HNO2, you'd know that this is a weak acid. So this is a weak acid. What that means is this is not going to break down 100%. Some HNO2 is going to remain as HNO2, and a small amount of that is going to break down into H plus NO2 minus. And that's how they are going to go in solution. The small part would break down into H plus and NO2 minus. Now I'm adding sodium nitrite. Let's see what it does. Again, as I just mentioned, group 1A, 2A salts, mostly they would break down 100%, especially when you have sodium, potassium, calcium. So in this case, sodium nitrite. So sodium will be separating from NO2, 100%. So that means there will be no such equilibrium. It will be sodium plus NO2 minus. So completely dissociates 100% because of sodium. Almost all sodium salts, potassium salts, they break down 100%. So this will break down 100%. Now what is the common ion here? I have these two ions the same, that's why it's a common ion. And indeed, this is going to change the equilibrium. So as soon as there is an increased amount of NO2 minus coming from sodium nitrite, basically we're increasing the concentration of the product of the first equilibrium. Now we can apply Le-Chatelier's principle. When you're increasing this concentration, it will try to decrease it by moving from right to the left. What that means is that's going to consume H plus. So H plus concentration, because of this common ion effect, would go down. So because of the common ion effect, equilibrium will be shifted from right to the left. That's going to consume H plus. When H plus is being consumed, so its equilibrium concentration would go down. Going down, H plus concentration means OH concentration would go up, and pH is going to go up. So basically, because of this common ion effect, pH would go up. So make sure you prepare this kind of questions, and there are a number of examples in the book. You can pick some of those problems, and for your practice, you should do them. And that will prepare you for this exam. The next question I would like to discuss would be percent ionization of a weak acid. I just mentioned that weak acid doesn't break down 100%. So often I ask this question in exam, that what percent of a particular acid would break down, or what percent would be ionized. And that's the calculation that I'm going to show you now. So percent ionization of a weak acid. So percent ionization of a weak acid. For going over this example, let's assume that I have 0.10 molar acetic acid. This is an organic acid, and you must know the Ka value, and the Ka for this acid equals to 1.8 times 10 to the negative 5. Okay, and we need to get percent ionization. Okay, now how do I do it? Acidic acid. First you need to think that is it one of the strong acids? Well, I told you to remember strong acids, HCl, HBr, HI, HNO3, those are strong acids. So this is not one of those acids from the list. And so it's a weak acid. So I can write down, I don't have to know the formula, so I can write down as HA as the symbolic formula for this acid. So let's assume that I have 0.10 of HA. So let me show you how it is going to break down. HA is going to break down as H plus A minus. There'll be no 100% breakdown because this is a weak acid. So initially, let me show you how it's going to work. Initially, say I added 0.10 molar of acidic acid, a weak acid. So let me write down here, weak acid, so that we know only part of this will break down. At the very beginning, it doesn't get time to break down because it takes some time, and at that time, you had 0 H plus and 0 A minus, which is the breakdown product. In terms of acidic acid, this is acidic acid, this is H plus, this is acetate ion. Since you don't need to know the formula for this particular course, you can write down as A minus as acetate ion. At equilibrium means if you wait long enough, there'll be no more changes in concentration. A part of this, before it reaches equilibrium, part of this is going to break down. Let's assume that X is that quantity. So the leftover is going to be 0.10 minus X. And the leftover amount is called equilibrium concentration. Now this is how you need to look at it. When one molecule of HA breaks down, you get 1 H plus and 1 A minus. If I have X breaks down, then you get X here, X of H plus and X of A minus. So make sure you can set it up like this. Now, equilibrium constant, I'm going to write it down as Ka. K equilibrium would be Ka. Now why A? A for acid. Just by looking at the right hand side, which has H plus, that tells me this is an acidic reaction. If I have both H plus and OH minus on the right side, it's neither acidic nor basic, it will be Kw, which is water, basically, equilibrium constant of water. But in this case, it's Ka. If I had OH minus on the right side, it would be Kb, basic equilibrium. So I have Ka, and that's equal to X times X, these two numbers on the top. So X times X divided by 0.10 minus X. So basically I can write down as X squared by 0.10 minus X. And I'm going to write down Ka value, which is given 1.8 times 10 to the negative 5. This is the quadratic equation. You have two alternatives. Those of you have a calculator to calculate X value, and you can use it, program it so that you can quickly solve for quadratic function. Or you can make a simpler expression by ignoring X. So this involves an assumption. Assume that 0.10 minus X is equals to 0.10. Now that's true when X is very small compared to 0.10. And how small is very small for this assumption? We normally say it should be less than 5% of this number. So if it's less than 5% of this number, then you can make this assumption and your answer will not be much different if it's solved by quadratic means. But this is going to save you time once you make this assumption. And later on you need to check back whether indeed it is less than 5% of 0.10. Now once I make this assumption, I can reorganize this whole expression. 1.8 times 10 to the negative 5 equals to x squared by 0.10. Now, this would give me, because I ignored x here, so this gives me x squared equal to, you multiply both sides by 0.10, so that would give me 1.8 times 10 to the negative 6. From here, I can find out x value, which will be the square root of this number. So, that gives you 1.34 times 10 to the negative 3. So that's the value that I got, but you should double check my numbers. 1.34 times 10 to the negative 3. And the question is, what is that x value? What does it stand for? Look at this. This is the amount of HA that broke down. That's also the amount of H plus that we got. And that's what we're interested in. So that's H plus concentration at equilibrium. So the question is, how do I get percent ionization? Let's do that problem now. That percent ionization will be given by X is ionized, or how much H we are getting, H plus we are getting, divide by the initial concentration, which is 0.10, times 100. So how much of HA broke down, which is X, divided by initial concentration times 100, and that gives you percent ionization for this particular compound. And X value we got is 1.34 divided by 0.10. 0.10, this is 10 to the negative 3. This is 0.100 times 100. I got 1.31%, 1.3%. Again, you should double check my numbers. It will be a good practice for you. So let me review this. This question gives 0.10 molar of weak acid and Ka value is given. Question is, what will be the percent ionization? Percent ionization is what percent of the original acid would break down. And we are assuming that to be X, and that gives you X of H plus and X of A minus. Then you set up an equation, that's Ka. Then you solve it by ignoring X here. And finally we solve for X, which is 1.34 times 10 to the negative 3. And that's pretty small compared to 0.10. So our assumption is fine. We don't need to solve by quadratic method. So percent ionization will be given by percent that broke down, the amount that broke down, divided by original concentration times 100. So that gives about 1.34%. The next problem is on buffer solution. And in calculating pH of a buffer solution, we're going to use Henderson-Hasselbalch equation. These are the names of scientists. Okay, that basically tells you that pH of a buffer solution will be given by pKa plus log of conjugate base over conjugate acid. Now let me briefly talk about buffer solution. What is a buffer solution? This is a solution that doesn't change its pH or H plus concentration when you add a little bit of acid or a base to it. So these are going to maintain its pH or H plus concentration. Now, in this particular case, I must say that a buffer solution, you make it by adding these two things. Weak acid plus salt of weak acid. Weak acid and salt of a weak acid. Weak base plus salt of weak base. Example, acetic acid and sodium acetate. Or in our symbolic formula, you can write down as HA and sodium A. So weak acid and salt of that weak acid would give you a buffer. Or weak base could be ammonia or amine. We often write down as RNH2. So weak base would be ammonia plus salt of a weak base. It can have ammonium chloride, for example. Okay? And keep something in mind that these are always conjugate acid-base pair. This is the conjugate acid part. This is the base part. By removing H plus, you get this. And in this case also, HA, by removing H, you get A minus. Because sodium is going to be separated completely from the rest of the molecule. Now, just to give you an idea why it acts as a buffer solution. Let me just give you an idea about why it works as a buffer. Say I have a mixture of HA and sodium acetate. Sodium would be all separated. So it's going to be sodium plus A minus. Sodium plus A minus. Okay? Now why I separated sodium? Because sodium, potassium, they always break down 100%. This is a weak acid. It would not break down 100%. Most of it remained like this. Now, a mixture like this would give you a buffer solution. The question is, why? Say I'm adding a base. The base is OH minus. When OH minus goes in there, if I add only one OH minus, as an example, it's going to grab this H plus. So OH minus is going to be grabbed by this H plus. So you are not going to see the effect of OH minus because there is something to grab or neutralize that OH minus. And that's why there will be no change in pH as long as I have some HA already there. Similarly, when I'm adding H plus, is there anything to combine with this? Yes, A minus is going to combine with H plus. So even though you're adding an acid, you do not see the effect of an acid because there is something which is grabbing that H plus quickly. So A minus is going to grab H plus and become HA. So as long as something like this happens, there will be no change in pH. Because in order to have a pH change, you must have additional H plus or additional OH minus in the solution. But in this case, it cannot happen. Now, if I have very few HA and A minus, after you run out of all HA, yes, it's going to be more basic when you're adding OH minus. So in other words, if I have a lot of these HAs or A minuses, I can keep on adding acid or base from the top, and it can maintain its pH for much longer. And that's a buffer with high capacity. So in order to get high capacity, you must have large concentration of weak acid as well as large concentration of salt of a weak acid. Or in case of a weak base, large concentration of weak base and large concentration of salt of weak base. So make sure you understand why these act as buffer solutions. So now we're going to do a few calculations on buffer. The first calculation I would like to do would be for this particular compound. Say I am adding 0.20 molar acetic acid, HA, at 0.25 molar sodium acetate. Again, these are all this is organic acid, and that's a weak acid. It's not one of our known acids, known as strong acids. So the question is, would this make a buffer solution? Answer is yes, because this is a weak acid, and this is the salt of a weak acid. And that gives you the conjugate base. Just to remind you this, sodium would break down 100%, it would get separated, and you'd end up in having a minus in the solution. So you have conjugate acid, this is the conjugate base. And we can now use Henderson-Hasselbalch equation to calculate pH. So pH of this solution will be given by pKa. We need to have the Ka value for this acid, which is acetic acid in this case. So let's write down Ka. Ka is 1.8 times 10 to the negative 5. That has to be given to you. Okay, now let's do the math. pKa, just like pH, this is a minus log. And that's the Ka value plus log of concentration of conjugate base. In our case, conjugate base is A minus. That's coming from sodium NaA. Since sodium gets separated, we don't need to worry about it. And then at the bottom you'd have conjugate acid, which is HA. Now, minus log of 1.8 times 10 to the negative 5 plus log of, let's put down numbers. Now we got HA, which is 0.20. At the bottom we have 0.20. And on the top we have A minus, which is 0.25. Now let me explain to you, in case you are confused here, that how I got this same number. Sodium acetate is going to break down 100% because it's a sodium compound. So when I have 0.25 molar, at the beginning it doesn't have chance to break down, but it will quickly break down 100%, so you'd have nothing left here. When one sodium acetate breaks down, you get one sodium plus one acetate ion. When 0.25 breaks down, it will be the same number here. And that's why I have used this number. So make sure you understand this. Now if you do the math, your answer is going to be 4.84. You can, as I said, you can always double check my calculation. 4.84. That's the pH of a buffer solution when you add 0.20 molar acetic acid, which is a weak acid, and 0.25 molar sodium acetate. This is the weak acid, this is the salt of the weak acid. Or you can say this is a weak acid, this is the conjugate base of the weak acid. And you need that for a buffer solution. Let's make a change to this question. Now instead of saying that I'm adding 0.20 molar to 0.25 molar acetate, sodium acetate, what I'm going to do is now we're going to add 0.03 moles of HCl and see how it changes the pH value. So this is going to be slightly different from our previous problem. So let me write down this. pH after adding 0.03 moles HCl. It is still going to be a buffer solution because you'd see that these other concentrations are pretty large, 0.20 and 0.25. So what we're saying is we still have these two concentrations, but in addition to that, we are adding some acid from the top. We are adding how much acid? 0.03 moles of acid. Now what does it do? A minus plus HCl. We need to understand this reaction. That gives HA plus Cl minus. Now A minus that we already had A minus coming from sodium acetate, which is 0.25. The amount that you are going to get because of the breakdown of HA is very little, so you can ignore that because this is a weak acid. So initially we can just say, to make it easier, 0.25 molar, that's coming from sodium acetate, sodium salt, and 0.03 was HCl, and assume that this was added to the whole liter solution, so it's going to be 0.03 molar or moles per liter. So that's we are adding this, and then how much will be left over here at equilibrium? 0.25 minus 0.03. Because this is a strong acid, it's going to react 100% with A minus. And in doing that, when this much is going to react, and if one of these reacts, you're going to get one of these and one of these. 0.03 reacts, you get 0.03 here and 0.03 here. That's the additional quantity. So let me write down, so it'd be plus 0.03 here and plus 0.03 here. We don't care about Cl minus, but we do care about HA. Now we already have HA in the solution, which is 0.20. So initially we had 0.20 molar HA. So this is the additional quantity because of this reaction. So now our pH calculation would be as follows. Again, I'm going to use that same expression, pKa plus log of conjugate base over conjugate acid. So this is minus log of 1.8 times 10 to the negative 5, just like before, plus log. This time conjugate base concentration, which is A minus concentration on the top. Keep in mind, this is A minus, and this is HA. Okay, and now those concentrations changed. The top number is now 0.25. This is A minus, minus 0.03. And the bottom number is 0.20 plus 0.03, because they're adding. You got an added quantity. Now, if you do all the math, this is what I got, so you can always double check. 4.72 is the pH. And you can see, since this is a buffer, the change in pH was not that great. It almost remained the same. So this is how you can get pH of a solution after you added, in this case, a strong acid. You can also do similar calculation after adding a little bit of strong base. And again, in homework problem, you'd find quite a few problems like these. And I strongly suggest that you try. Next would be a qualitative question on buffer. Now let me give you an idea that how we can answer to those kind of questions. Say I give you a solution like this, HBr and add it to sodium bromide. Will it give a buffer solution? Let me write down here. Buffer solution. So if I add HBr to sodium bromide, are we going to get a buffer solution? Just by looking at it, you'd know that it's not, because this is strong acid. A strong acid means it's going to break down 100%. This is salt of a strong acid, so it's not going to give you a buffer solution. In order to be a buffer solution, you must have a weak acid, and salt of a weak acid, or weak base and salt of a weak base. So this is not going to give you a buffer. Because, keep in mind, you need to have a weak acid and a salt of a weak acid, because when you add H+, the basic part is going to grab that H+. If you have a strong acid, it's not going to happen. like that. Now let's try another one. Say I'm adding acetic acid and sodium acetate. So I can write down as HA and sodium acetate. Will it give you a buffer? Answer is yes, because HA is a weak acid and this is salt of a weak acid. Okay, so this is acetic acid, it's a sodium salt of a weak acid. So it would give you a buffer solution. So we'll have a question like this and make sure you recognize strong acid, strong base, weak base. That would be easier for you to come up with these qualitative questions. Next we'll be asking you a pH calculation at equivalence point when you do the titration. So pH at equivalence point. Let's assume that I have methylamine. This is called methylamine, CH3NH2. It's a base. It's a weak base. All amines are weak bases. Ammonia is one of them. So ammonia, methylamine, ethylamine, these are all weak bases. And you are adding HCl to that during titration. Remember titration, if something is coming from the burette and you have a compound and Erlenmeyer flask, so you have an Erlenmeyer flask, you have methylamine, HCl is coming from the burette, you get the end point when one is neutralizing the other. But question is, would you get the pH 7 at neutralization point? Not necessarily. It all depends upon what kind of product you get. Products can give you secondary reaction with water, making it acidic, basic, or neutral. In the first half of this review session, we talked about how to find out that information, that which salt gives you acidic, which salt gives you basic, and which salt gives you neutral solution. So let's do this problem. Let's assume that I'm adding 10 ml 0.100 molar of methylamine. I can write it down as RNH2. That way don't need to worry about actual formula. And I'm adding, if I have 10 ml of 0.1 molar NH3NH2, I would need 10 ml of HCl for same concentration. 0.100 molar HCl. If you calculate the number of moles, this is moles per liter, and if you change it to liter, get moles, we'd find that number of moles from this equals to number of moles of this. And that's how this reaction is going to happen. It's one-on-one reaction. It will be neutralized when these moles are equal. So I can write down the product for this reaction. CH3 NH3 plus Cl minus. In our symbolic formula, you can write it down like this: RNH3 plus Cl minus. Now, how does this reaction happen? H plus coming from here, it attaches to this pair of electron, and that makes it RNH3. And since this is coming as H plus, it becomes RNH3 plus, and Cl gets separated because this is a strong acid. It should give you this reaction, and this would be 100%. This reaction would happen 100%. So that's what you're going to see here. So if I have 10 ml of 0.1 molar of methylamine, I would need 10 ml of 0.1 molar HCl to completely neutralize this. My total volume is going to be double. 10 plus 10 is 20. So in my final solution, let's assume that they didn't have a chance to react. The final volume is now 20 ml. That means my volume is double, so the concentration will be 1/2 of this value. So it would be 0.050 molar, 0.050 molar of this. Now this is a one-on-one reaction. If I have 0.050 molar of this and 0.050 molar of this, at the end, there will be nothing left. I think I have not used the word final here. So when you add them together, the volume is double, the concentration 1/2. They are going to react, and nothing will be left here. So nothing left here, nothing left here. And how much is going to be left here? 0.050, 0.050. So that's the quantity that's going to be left. So when you do after you're done with titration, at end point, this is the amount of methyl ammonium ion you're going to get in the solution. It looks like you should be getting a neutral solution, but truly it's not, because this compound, which is a salt of this weak base, is going to give further reaction, and we call it secondary reaction with H2O, and that's going to make the change. And I'll show you how this happens. So let's use RNH3+. It doesn't really matter whether you use the actual formula or this kind of symbolic formula. RNH2 plus H plus. Question is, how do I predict this kind of reactions? RNH3 plus, this has already that hydrogen, extra hydrogen added, and so that extra hydrogen in presence of water would break down. Would not happen 100%, but whatever percent happens, it's going to make some changes in acidic or basic property. So now we can set up an expression like this. Initial, say, at 0.050 molar. It didn't have chance to do this reaction. At equilibrium, let's assume that X amount of this broke down. So you have left over 0.050 minus X, X here, X here. Now looking at the right hand side, I have H plus. So that's an acidic product. So I'll write down Ka for the equilibrium, and there'll be X times X, so X squared divided by 0.050 minus X. Now that's the Ka for RNH3 plus, or methyl ammonium ion. But this is coming from the weak base. Normally when you have a original basic substance, the book doesn't give you Ka value. They will give you Kb value for the basic form, not the acidic form. So if I give you this question in exam, I'll give you the Kb value. Let's assume that Kb value is given. Let's now, you need to find out that Kb, if Kb value is given, has to be given. Now, I'm going to assume a number here because I don't have the exact value from the book. So I'm going to assume that, say, Kb value is, normally these are small values. So this is 1.0 times 10 to the negative, say, 14, or negative 12. Now, how do I get Ka value? Ka will be given by Ka times Kb equals to Kw, which is 1.0 times 10 to the negative 14. So from here, I can find out Ka value for that expression. Now keep in mind, this expression is valid for conjugate acid-base pair. If this is the acidic form, this is the basic form. So, and that's Ka for the acidic form, Kb is for the basic form. So in this particular case, it's methylamine, and this would be the methylamine form would be Kb, and its acidic form, methyl ammonium ion, RNH3+, or CH3NH3+, would have the Ka value. Always, this expression works that way for conjugate acid-base pair. So from here I can calculate Ka equals to 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 12. And as I said, this is just my assumed value, has nothing to do with the right value. I can already see that this number would not be that high. But anyway, so you use Ka value here and then solve for X. it would be a good idea to pick some of these problems from the book for your practice and solve either by quadratic means, depending upon how small the x value is. Whenever the Ka value is pretty small, then it's a good assumption to ignore x from the bottom. If it is not that small, then you have to solve by quadratic method. Now let me write down one equation for quadratic in case you need to solve by quadratic method. Most of the calculators would do the job. And I'm assuming that in your math class you learned that using this solution of quadratic equations. So in very few of our problems, you are going to solve by quadratic method. But it's a good idea to know that ax squared plus bx plus c equals to 0. Then you need to find out x value is minus b plus minus b squared minus 4ac divided by 2a. So this would have two values. We only deal with the positive number, so the negative number would not be acceptable. So that's how you get the x value. B will be the coefficient of x, a is coefficient of x squared, so that's how you come up with this expression. But if you have one of these modern calculators, it will do that whole calculation for you. And you get a quick answer to that question. Now our next problem will be on solubility. The word solubility is mostly used for substances which are not highly soluble in water. Now let me give you a simple example of magnesium fluoride. Most of the magnesium compounds are soluble, but not the fluorides. So if I give you this question, that magnesium fluoride, and say solubility, again I'm making some of these numbers, solubility equals to 2.0 times 10 to the negative 2 molar. Say that information is given to you, and you need to get equilibrium constant, in this case KSP. So a partly soluble compound is added in water, and only 2.0 times 10 to the negative 12 goes in solution. Question is, what is the equilibrium constant, or KSP value? Again, remember that we use Ka for acidic equilibrium, Kb for basic reaction, and in this case for solubility product we use KSP. So let me show you how we can do a problem like this. Magnesium fluoride solid, you add it in the solution, and it's going to break down into Mg2 plus aqueous plus 2F minus aqueous. Initially, again, we'll have to assume that I have an A, is the initial concentration. It didn't have a chance to break down. Only part of this would break down. So at equilibrium, we said that X has broken down. If one MgF2 breaks down, you get 1 Mg and 2F minus. When X breaks down, you get X here and 2X here. Don't forget, it's 2 times more. So my equilibrium expression now would be, I'm going to write down K equilibrium as KSP, because it's the solubility product calculation. It's a good idea to first write down the basic expression, Mg concentration 2 plus raised to the power 1. These are the coefficients of balanced reaction. F minus raised to the power 2, these are all equilibrium values. And MgF2 raised to the power 1, but that's solid. This is a solid mixed with aqueous solution, so you can ignore it. This concentration doesn't change with time. So just ignore that. So I'm going to use this other value. So it's going to be X times 2X squared So I have 4x cubed. Now what is x here? X tells us how much of MgF2 broke down and went in solution. That's same as solubility. So basically this is solubility. Because unless MgF2 breaks down, it doesn't go in water solution. Water only gets these pluses and minuses when they're broken down, then and only then it goes in water solution. So we already calculated this solubility value, and by considering it to be x. Now that value is given. So just plug in that number. 4 times 2.0 times 10 to the negative 2 squared. I'm sorry, that's going to be cubed. So in this case, you're going to see there's 4x cubed, and it's going to be 6 10 to the power minus 6. This is going to be 32. 32 times, you should always double check my numbers, may not be right. So this is 3.2, this is times 10 divided by 10, this is 10 to the negative 5. So this is just a sample calculation. Make sure you try similar problems from the book. So when they give you solubility, that means they're giving you the x value, the amount that broke down and went in solution. My next problem would be the same on solubility in presence of a common ion. So let's use the same reaction of MgF2. Now we are adding something else to it, so that's what we're going to look at now. So the question is like this. I have MgF2 in water, and we know that it's not highly soluble, part of that will break down, and I'm adding in that solution MgBr2. The question is MgBr2 added. This is another question. Keep that in mind, it's not the same question. This is another question where I have MgBr2 now in presence of MgF2 in presence of MgBr2. Now what does MgBr2 do? Now let me write down this concentration. 1.0 times 10 to the negative 2 molar MgBr2. So basically I'm adding MgBr2 in MgF2. Now MgBr2 is highly soluble. It dissociates completely. So I must write down here, dissociates completely. Now when MgBr2 breaks down, it will look like this. MgBr2, Mg2 plus 2Br minus, and that will break down 100%. So you'd have 1.0 times 10 to the negative 2 to begin with. 0 here, 1.0 times 10 to the negative 2, 2 times 1.0 times 10 to the negative 2. Why 2 times? Because there's 2. This is 1, 1, 2 relationship. When 1 breaks down, you get 1 here, 2 here. When 1.0 breaks down, you get 1 times 10 to the negative 2 here, 2 times of the same quantity for Br minus. Again, we don't need to worry about these numbers at this time. Now what is the common ion here? That's what you need to look at. Mg2 plus. I have Mg2 plus. So initially, I would not say I have 0. Initially I have, when you add MgBr2, initially you'd have 1.0 times 10 to the negative 2. Let me clarify this. This is coming from MgBr2, which broke down 100%. And so initially we have that quantity, and X we are getting because of this breakdown. So now we need to write down expression for KSP. Now let's assume that I have the KSP value given in this case. This solubility we're not going to need. So for this question, this is the values given. Concentration of MgBr2 is given, which is 1 times 10 to the negative 2. That is added to MgF2. And KSP value, in this case, is given. Let's assume that that value is 4 times 4.0 times 10 to the negative 12. Again, I'm just making up this number. Is given. KSP for MgF2 is given. 4.0 times 10 to the negative 2. The question is, what is the solubility? And first example, we gave solubility. You have to calculate KSP.